Hello there, Year 13. So, we're going to look at special relativity, and for large portions of this video you will not understand. The common phrase in physics is if you're not confused, you haven't understood it. You should be confused. Fundamental common sense notions on how the universe works are going to be challenged, and you're going to see that actually they were wrong. So it's okay to be confused. Re-watch the bits you don't understand. Arrive on the lesson on Tuesday knowing which bits you need me to explain further, but it's okay to be confused. We're going to start off 1890, I've wrote the date down, I haven't, 1896, 1897. Michelson and Morley were trying to prove the ether. So it's at the end of the 19th century. We were pretty confident we knew everything about physics. We had a classical model of how waves worked that we were pretty happy with. There was one lingering question: well, what did the waves travel through? What was the medium by which they propagated? And the belief was they travelled through something called the ether. You've probably heard the word ether, and that's where we get ethereal from. And we use it in day-to-day language to mean this kind of intangible, you can't see it, you can't touch it, you can't feel it substance that everything exists through. And it comes from this physics word, the ether. So they believed it was this intangible substance that all waves propagated through. And what Michelson and Morley were trying to do was prove it existed by looking at the speed of light. So they felt that the sun will move through the ether, and that if light was travelling parallel, it wouldn't be affected by the ether. If it was travelling against the ether, they felt light should be slower. So they set up something called an interferometer, which splits light up into two separate parts and recombines it again. So this animation here shows an interferometer working kind of at rest in the laboratory. Light leaves this source, is split up, bounces off these mirrors, is recombined and arrives here. Now they felt the light travelling perpendicular to the ether wouldn't be affected, but the light travelling parallel to the ether would be affected. And they thought the light travelling parallel to the ether would be slower. So they felt when the Earth was here in spring, there would be a difference in the speed of light. Now you might need to imagine this twisted at 90 degrees compared to my diagram here. But they felt this should happen. Light should leave, it should be separated. In this situation, the red light would be perpendicular, it hasn't been affected, but the blue light, which is travelling parallel, would be slower, and they would be able to see a difference in when the light arrived back at the mirror. And that difference would prove the ether existed. So they did this experiment, they took readings multiple times around the year, and actually they had what's called a null result. They found out that there was no difference. It didn't matter where this equipment was orientated. It didn't matter if it was upwind or downwind or left or right or parallel or perpendicular. Whatever happened, light recombined in the same way. They set out not necessarily to prove the ether existed, but to test the hypothesis of the ether, and they got a null result. They found that actually we don't know if it exists or not. Fast forward 10 years to 1905, and young patent clerk called Einstein is wrestling with some ideas about what happens as you approach the speed of light. Now our textbooks always show that experiment leading into special relativity. Actually, there's not a massive link. There's no historical document that says Einstein looked at Michelson and Morley and developed his theory. It started people thinking about light differently. If you disprove the ether, what else is wrong? Maybe other parts are wrong. But there's no definite link between those two experiments. Einstein came up with a thought experiment to try and explain what would happen when two objects are moving relative to each other. Now the belief was, if you had, I'm going to draw a car because I can't draw a train. if you had a car, and if you had a torch on top of the car was stationary, then the light would be travelling at the speed of light. If the car was moving at 0.1 the speed of light, well, if the car's moving at 0.1 the speed of light must be moving at 1.1. So you've got the speed of a light and you've got added to it the speed of the car. Equally, if the car is going at 0.2, should be travelling at 1.2. Logical, sensible, completely and totally wrong. They'd had some limited experiments, and just like the ether, we'd started to notice that actually it didn't matter what speed the object producing light was travelling at, we always measured the speed of light as the speed of light. This is the fourth experiment Einstein came up with. He said, imagine a light clock. So if we've got two mirrors, and if we say, we won't say seconds, we'll invent our own unit of time. One unit of time, call it the H, is the time taken to go from here to here. And this blue arrow here represents the path of a photon. So he said two people could have two light clocks that could set the photon off at the same time, and if they were stationary next to each other, they would agree on what one Hodge was, what one unit of time was. They'd agree on what the unit of time was. The problem came if one moved relative to the other. So let's say this clock remained stationary and this light clock got onto a train. Lots of trains in the thought experiments got onto a train. This chap would be stationary, this one will be moving relative to it. So as far as X is concerned, if he looks at it, the path of light that Y takes is a triangle, because as well as the light moving upwards, we've got the lateral motion of the train, and so we would see light take a different path. In itself, that's not a problem, because classically they said, well, we've got the speed of light, we've got the speed of a train, basic trig, let's add them together, light will be going faster. Except we found that it wasn't. Now the leap of faith, if you will, Einstein made, was to forget about time being this constant. He said, well, what if it's the time that's changing? We're measuring the speed of light as never changing. So let's, for a second, just accept that the speed of light doesn't change. So here, we've got speed equals distance over time. And here we've got speed equals distance over time. Now if we say that speed is light, and that for both those situations, the light is travelling the same speed. The speed of light hasn't changed. So this is a constant, and that's a constant. They're not changing. They've got to be equal to each other. But over here, we're travelling a bigger distance. So now we've got a problem mathematically, because our speed of light hasn't changed, but we're travelling a further distance. The only way to solve that problem is if the time gets larger. And when I say time getting larger, I mean the units of time get bigger. So this chap might experience 1 unit of time. What this chap calls 1 unit of time will be bigger compared to him. And I'm not certain I'm explaining that as clearly as possible. We're going to watch another animation. I'm going to try and say it in a different way. Hopefully one of them will trigger you. Now there was a factor, it's called the relativity factor, sometimes called the gamma factor, that affects how much this changes by. And that is... I always forget this. I'm just going to check in my notes for a second, sorry, I'll be back. we go, I've got my notes there. Sorry about that, year 13. So, it is one... Where did that come from? So, the relativity factor, so we're gamma beta, is 1 over root 1 minus v squared over c squared. V squared is the speed at which you're travelling relative to the object. And the key here is the word relative. It's all about relativity. Because the stationary person thinks time is going slower for this guy, but this guy thinks he's stationary and time is going slower here. They're relative compared to each other. Now, the bigger V gets, the more pronounced that difference is. We're not going to worry about the maths too much at this stage. That's what the calculations we're going to be doing in our lesson. I want you to get the concepts behind it. But this is the factor by which speed changes. Put some random numbers in. Look at half the speed of light. Look at 0.75 the speed of light. Look at 99% the speed of light. See how it affects gamma. So, I promised you we'd look at it in a different way. So, similar situation to what I've just been talking about. So if the clocks are stationary relative to each other, then you can see they always show the same time. Now if one of them is moving, then here's what I was talking about before. The path light takes gets more diagonal. So in this case, Jill reads 10 seconds, Jack reads 10.1. So in other words, as far as Jack is concerned, time is going slower for Jill. The light has travelled a further distance, the speed hasn't changed, but the time has. Let's make the speed a bit different, a bit bigger. So we're up to nearly 30% the speed of light, and we've still only got a difference of 0.4 of a second. Let's see what happens when we crank it up a bit. So, at 75% the speed of light, we've got a difference of half again. So, Jack has experienced 15.5 seconds, Jill has experienced 10 seconds. Now what always got me, what I really liked about relativity was its symmetry. Because as far as Jack is concerned, Jill is moving relative to him. If you've ever been in a train, just as it starts to pull off, as far as you're concerned, the rest of the world around you is going backwards. You think you're stationary. It's all about frames of reference. So Jill, as far as she's concerned, she is stationary, and time is going faster for Jack. Where's my evidence? Surely this is nonsense. Well, my evidence comes from muons. In the upper atmosphere, cosmic rays collide with the top atmosphere and they produce muon particles. We can produce them in the laboratory as well, and we can measure their half-life in the laboratory. Now, from our predictions, of the muons that are created at the top of the atmosphere, the vast majority should decay before they reach the ground. So I'm making these numbers up. Let's say it takes 1 second to reach the ground. and their half-life is thousandths of a second, then the vast majority should have decayed and never reached the ground. But we receive, and I wouldn't read too much about these mathematics, I don't know why I've included them, we receive a lot more muon particles than theory suggests we should. And it's because the muons are travelling at 98% the speed of light. So time is massively dilated. We call it time dilation. The fact it's slower. We think we are stationary. Relative to us, the muons are travelling at very close to the speed of light. So time travels slower for the muons relative to us. I'm pausing for effect here. Time travels slower for the muons. So what should take them a certain length of time, and they should all decay, actually they don't. And the reason they don't decay is because time's travelling slower for the muons, because they're travelling so close to the speed of light. We're going to do the maths on this in Tuesday's lesson. It's going to make more sense then, but you will see it 5, 6, 7 decimal places. This experimentation matches special relativity. We go back to Feynman. You can have the prettiest theory you want. If it doesn't match results, it's not worth a damn. Special relativity has both. It's mathematically elegant, it's mathematically pure, it's beautiful, and it matches experiment. It ticks all the boxes. We're going to go back to gamma for one last thought. What happens if these muons travel at the speed of light? So 3 times 10 to the 8 squared over 3 times 10 to the 8 squared. Try and figure out for me what the gamma factor would be when it's travelling at the speed of light. Okay, hopefully it said math error. 3 times 10 to the 8 squared over 3 times 10 to the 8 squared is 1. 1 minus 1 is 0. The square root of 0 is 0. 1 over 0 is infinity. Oh dear. So if we travel at the speed of light, time dilates to the point of stopping. Time will stop for that particle. And I haven't mentioned that mass increases and length shrinks as you approach the speed of light. So not only would time be 0, but you would have no length, and you would have an infinite mass. So we've got an infinite mass taking up no space, that's infinite density, and time has stopped. Can't happen. Maths won't let it. I suggest you re-watch this. I think I wasn't massively clear about the light clocks, but think about how the motion of the train going sideways adds on to the path the particle takes. It's logical the speed of light should increase. It doesn't. That means something else has got to change. That's why length contracts. That's why time slows down. One message I want to leave you with is that these aren't fancy string theory, oh maybe this is true. This is hard, measurable, comparable physics. This is real. I'm not certain I understand why it happens. I kind of accept that time isn't the same for everybody. It doesn't trouble me too much, and so in my head I think of that as understanding. I don't know if it is. So I don't expect you to come in on Tuesday understanding relativity. If you've only got a few questions, that's a massive win. Rewatch it, see the hard parts again. If you're not confused, you haven't understood it. Okay, thank you.